superficially, these guys look pretty much the same as they did before. I turn them on the same way. And Bluetooth control via app. So, hitting this phone app, and I can do all kinds of stuff. But internally, the guts are actually quite different. One of the big things that I can do now is, imagine you don't want to deal with the watch. When I push the button on this guy, you'll notice that I can make them move together just by hitting the button, which means completely without an app, the different pen lights can all be synchronized. Plus, there's a whole component that's not here anymore. There's no more relay box sitting between Bluetooth and RF modem. And that's because internally, the circuitry and all the code is actually pretty new and different. So let me take a look. Let's take a look here and see what these key differences are. So these two green boards down here, this is the previous edition, right? Which for the last couple of generations has been the same design. Bluetooth-based app connecting to a relay box. Relay box can talk Bluetooth and has a CC1101 RF transmitter, and then there's a pan stamp here. Pan stamp is basically Arduino with a CC1101 that's going to then receive on this 900 megahertz and is going to process those commands and set the LEDs to whatever whatever the command is. In the latest design, right, I did update the design to have an IPEX connector, but fundamentally then you need two solder-on modules. One is the pan stamp, and then one is this regulator. Regulator needs to be set to kind of this odd 4.2, 4.3 volts-ish, and so I have to use this potentiometer-controlled thing. And this was actually pretty annoying. I designed this with 0402s, designed to be assembled by PCBA House. I used Seed Studio. They've been pretty reliable for these prototype quantities. This is what one of the boards straight from Seed Studio looks like. Solder on the pan stamp, no big deal really. This is actually pretty easy. And then I have to set up the regulator, and that's kind of annoying and fiddly to control this potentiometer precisely and then keep it from moving, gluing it down. And then actually this potentiometer thing here moves a bit no matter what, and then I have to got a weird technique to through hole this without having the pins stick too far off in the back. And so this regulator thing was annoying, and I also pan stamp upgraded, and now they are up to the pan stamp 3. They don't make the pan stamp 2 anymore. The pan stamp 3 is a much larger form factor than this that comes only in a version that has an integrated RF amplifier. Good for the relay box, but suddenly there's no way to make any more, no way to acquire any more of these. I do have a stock, but then nobody else would be able to build them. And so I decided to do a significant redesign here in the updated board. When you compare, it looks kind of similar. The connector here for the LED is the same. I still have the JST connector for power switch, button, the TLC 59116 for the LED driver, but now no more through-hole regulator, and I've got instead kind of a much finer pitched module, because now I'm using an ESP32. ESP32 has Bluetooth and Wi-Fi built in, and comes in this convenient form factor, this Room 32U form factor that has a little IPEX header on it for a 2.4 gigahertz antenna. And this guy here, since it's a relatively low-level component, easy to source, probably not going to go out of print anytime soon. Updating this board kind of necessitated a couple of also significant board redesigns. So while the top part is very similar, the bottom part here, especially this section here, is really different. You'll notice no more weird 6-pin header here. This was kind of an exotic component. Now there's a micro USB. Micro USB then is connected to this CH340. CH340, famous USB UART. That's then connected to the ESP32 here. ESP32 has this thing where you've got to fiddle with the GPIO pin, so you need kind of like a double latch. That's this component here that then allows me to program it without needing any buttons. And then to get rid and for power and to get rid of the module, I've got a 3.3 volt LDO here. Similar to the LDO, this is an LDO here, also a 3.3 volt. This one is a bit more powerful because the ESP32 needs more current in order to run its, in order to run the wireless, since it has to transmit. And then there's a whole power regulator kind of built in here. So I'm not an electrical engineer, pretty terrible with analog or linear circuits. But Texas Instruments has a pretty cool online tool where you can put on the different power specifications you want for a switching power supply, and it'll spit out the BOM and a design for you within that specifications. So there's a switching power supply here. There's the inductor for it, and then a couple of small passives, capacitors and stuff around here. And then there's these two big components. There's a MOSFET here for reverse current protection. Because this will get plugged in directly to the computer, the protection needs to be here on circuit. And there's a diode here. This other big guy here is a diode, and that prevents current from flowing back into the USB when you're plugged in. When the USB is plugged in, the USB will power the whole power the board, including power the regulator. So the MOSFET and the diode together kind of make sure that the power pads are correct, and then this regular design with pre-populated components, then make sure that rather than this fiddly potentiometer, the voltage on all the boards is exactly the same. This board here is significantly simpler to assemble. Just having less steps, it makes it much easier to assemble despite having more pins compared to the older version. So where then in this picture does that give us the kind of the two big new features, which is the direct peer-to-peer, no app-based button synchronization between the different boards, right, that I get here, they all move together. And how do I get rid of the control box? The magic for all of that is really in the code. So we can take a look here at the code for the ESP32, and what we see here, and let me get rid of the terminal in this window. I was just flashing one. Main thing here is the ESP32, right? Everything's controlled by the ESP32 modem and all the wireless and all the Bluetooth. It's all on board in the ESP32, so everything's all in one single code base. For the communication between penlights, I'm using a Espressif specific capability called ESP-NOW. ESP-NOW basically broadcasts an 802.11 compliant packet, but allows the sticks to communicate without having one stick be the AP or having to connect to an AP. Rather, even in station mode, everyone will kind of pick up this connectionless packet in ESP-NOW. Process is pretty simple. Tons of sample code on this, right? I've set every stick gets the same code. They all get set to Wi-Fi STA, right, station mode. They're all set as clients. There's no access point. I set the protocol. I'm using the Espressif LR protocol. Not really getting any different performance than 802.11b, but supposedly they'll be making enhancements. And LR is fine. It's relatively low bandwidth. And then I set my send and receive callbacks, and then configure up the peer to the station. Now the peer is hard-coded because what matters is just the broadcast. And so while some code samples you'll find will have this mechanism by which the peers have to discover each other, like, they broadcast occasionally and they pick each other up and then register and do this peer registration, the ESP-NOW add peer call based upon listening to broadcast. I don't need to do that, right? The peers actually don't need to register them each other directly, because all I want to do is I hit the button, broadcast a message, everyone listening, change your color, right? And so the only peer that everybody needs is the broadcast address. Magic then, both for improved range, because much less powerful because I don't have the relay box, is there's also this mesh-like retransmission mechanism. And most of that magic is in the receive callback and the processing there. So let's take a look at the receive callback, right? The API here is really simple for dealing with this, right? Broadcast message appears, and therefore then receive callback will give me this this byte array, this UART data array. I deserialize that into back into the command, and then I basically a couple of different possibilities for commands. The command now carries a sequence number, and the sequence number is what I use for retransmissions. Because buttons are peer-to-peer purely and there's no single controller, buttons all come with sequence number 0, no sequence number, so no resend or whatever. But commands that come from Bluetooth will carry with it a sequence number that's incremented. It's not being tracked by the app. It's actually being tracked by whichever stick connects to Bluetooth, will then keep track of a sequence number. And so after deserializing this and getting the sequence number, I do drop it into a queue because the ESP32 is dual core. And in Arduino configuration, Wi-Fi runs on one core. The rest of the Arduino code runs on a different core. This is the Wi-Fi callback. I think it ends up running on a, maybe end up running on the Wi-Fi core. Not exactly sure, but it doesn't really matter. You don't want to do a huge amount in this callback anyway. So I enqueue it and then dequeue it back in this tick, which is called from the loop. And that ensures that I know exactly where the processing comes from. I receive the command off the queue, and then if we process the message, meaning the sequence number is bigger than the current sequence number of the known to the individual penlight, then it'll retransmit the message. That does mean that there'll be a flurry of retransmits. For every penlight that's in range, but the reality is the single packet here is pretty small, and so if I have 6 penlights, there'll be 6 packets going out, right? The original master will send 1 packet, and then the remaining 5 will each send a retransmit if they all see the message. But that's actually a relatively small amount of traffic. Really, no big deal for the available airspace bandwidth, and that means that sure, if the controller is in one location and all of the other penlights are all far away, this isn't going to work. The signal is just not as powerful as it was with the relay, but with the retransmits, a sequence of penlights, or even possibly just like non-light relays, would be able to retransmit that signal arbitrary distances, although with some latency. And so this gives me an improved range without having to deal with the issue of amplifiers. It allows me to not have the relay. Bluetooth actually initializes pretty much the same code as it was for the relay box, but now the code is on every single stick. Basically, when the sticks initialize, we'll take a look at the Bluetooth initialization here. Relatively simple. When the sticks initialize, they all initialize their Bluetooth stacks. They all begin advertising, but the app, of course, is only going to connect to one of them. And once any stick receives a message off the mesh, it'll shut down its Bluetooth network. And so the initialization sequence is going to be something like you turn on one stick, connect the app, and then turn on the remainder, or you turn on all the sticks, the app connects randomly to one, and then it'll shut down the rest, because then you won't know which stick is the master. Or if you somehow are in peer mode, then you will have to power cycle the stick in order to reactivate the Bluetooth and then connect the app to it. Latency here is actually quite good. And so if we look at this and I get back to the app here, let's say let's turn off a light here. I've got the app here, right? Responsiveness, pretty much it's hard to tell which one of these is the master. Right? I can immediately pick a color. If I go to the fastest, like my strobe, there's no noticeable latency between the master and the slave. The ESP-NOW is very, very efficient, very low latency. And this actually is kind of a stress test for the network because they're so close to each other. They're actually way too close to each other. The actually ideal distance between these is actually a couple of feet apart, but really no problem at all with this. If we take a look at a fully assembled board, kind of as the last piece here, I've got one down here. The main difference here now for the fully populated board compared to the bare unassembled board, I've got the heatsink here. I do have a heat spreader on top of the whole power array. That whole power section doesn't technically need it, but this lowers the overall temperature. So there isn't like a hot spot. There can be a hot spot that can get to like 80 something degrees Celsius if you run really like max brightness continuously. This lowers that hot spot across all of the different components, right? The MOSFET generates a little bit of heat. The regulator generates some heat. This takes care of all of that. And then I've got the IPEX connector here. IPEX connector kind of winds around the front and then hits this 2.4 gigahertz, this PCB antenna. PCB antenna, 2.4 gigahertz PCB antenna is not exactly cheap. It's not like cut wire, but it's fairly cheap. You can't find really cheap ones on DigiKey. All of those cost like whatever $5-7 a piece. But Adafruit's got a couple of good ones, or has a good one here that's just it's less than $1 a piece. And so these are pretty reasonable. Then for me to say, hey, I want to use the IPEX connector compared to what I ended up doing with the PanStam version, which is turns out that the best performance was from a wire, but buying wires attached to IPEX, this thing was also ridiculously expensive, right? Like a $9 or a $12 component. And so I ended up bypassing the IPEX connector and soldering them on. No need to do that for the 2.4. The 2.4 is reasonably economical on its own. And so that's about it. Everything's all checked in. Handles and everything are all still the same.